5 different skeletal muscle cells here. Each of these will have to be told by a neuron to generate an action potential and contract. Here we have quite a few cardiac muscle cells. But if we start an action potential in one of these cells, it will be conducted to all its neighboring cells. So the heart essentially forms one electrical unit. It's as if I send a signal to my biceps brachii to one cell of the biceps brachii, and it tells all the other muscle cells in the biceps brachii to contract. Well, of course, it doesn't in the biceps brachii, but it does in the heart. Because the muscle cells of the heart are all electrically interconnected, so they can pass the action potential from one cell to another. Here's a drawing of the muscle cells of the heart. Here is a cardiac muscle cell. There's another cardiac muscle cell. There's the nucleus of each cell. You can see they're shown as striated here. And what you can also see are these structures here. Wow. Too many glasses of wine. Those are called intercalated discs. But what they really are electrical synapses. Well, earlier we studied chemical synapses. Remember when, say, a motor neuron releases acetylcholine onto skeletal muscle cells, and that causes the generation of an action potential in the skeletal muscle cells, and then you get contraction of the skeletal muscle cells. That's a chemical synapses. Most of the synapses in the nervous system and between the nervous system and the muscular system are chemical synapses. But in the heart, what dominates are electrical synapses. So that an action potential in this cell will be passed right on to the next cell without the intervention of any chemical intermediary. So they call them intercalated discs, but they're really electrical synapses. There's no 5 steps of synaptic communication. There's just the electrical signal, the action potential, moves from one cell right into the other. So you start an action potential in one part of the heart, and it gets spread through all the rest of the heart. In fact, that's how it works. Here you're looking at the electrical conduction system of the heart. It begins over here with the SA nod. No, that's what you're about to do. You're about to nod off. Actually, no, but what happened? I know that it should be there, but it wasn't there. The SA node, that's a region in the posterior wall of the right atrium where there are a few hundred cells that are not contracting cells. They don't contract. What they do, though, is generate action potential. If your heart is beating 60 times a minute, and I'm saying it is, but I said if, that means there's 60 action potentials coming out of your SA node every minute. That is about 1 every second. The SA node is sometimes called the pacemaker of the heart. And it's why we don't need neural innervation of our heart. Now, we do have neural innervation of our heart. We don't need neural innervation of our heart, as people with heart transplants will tell you. Ask Steve Chan. Don't believe it. They cut away the neural innervation when they cut out his old heart and dropped a new heart. The new heart had an SA node. And the SA node will keep the new heart contracted, even if the nervous system isn't connected to the new heart. So, this bundle of cells here in the posterior wall of the right atrium is the pacemaker of the heart. It generates action potentials about every second. An action potential flows out of the SA node, sweeping over the atria, causing the atria to contract. As the action potential sweeps over the atria, causing the atria to contract, it heads to the ventricles. But there's only one pathway the action potential can use to get to the ventricles. That pathway is right here in the wall between the two sides of the heart, the septum that separates the two pumps. This is called the AV node. Suppose you wanted to go to North Kansas City. You go to North Kansas City, you got to cross the Missouri River. And there's only one bridge, let's say, across the Missouri River. Well, if you want to get to North Kansas City in your car, that's what you're going to have to use. You're going to have to use that bridge across the river. Your car can't swim. Likewise, if you want an action potential to get from the SA node to the ventricles, the only way you can get there is to pass through the AV node. It's the only electrical bridge that connects the atria to the ventricles. AV, of course, stands for atrioventricular node. But there's more to it than simply serving as the only electrical bridge from the atria to the ventricles. It also slows down the action potential, giving the atria time to finish their contractions before the ventricles contract. The AV node is kind of like the speed bumps out in the street. Except, of course, the speed bumps in the street are fixed in height. They don't change. But they're there to slow you down. The AV node is like a speed bump, except that speed bump can be raised, it can be lowered. You raise the speed bump, it'll take longer for the action potential to get to the ventricles. Your heart rate will slow down. If you lower the speed bump, the action potential will get to the ventricles more rapidly. Your heart will speed up. So we can change the rate at which the action potential moves through the AV node and thereby change heart rate. The AV node has a third function too. I love things that have three functions. It serves as a backup pacemaker in case the SA node isn't doing its job. For some reason, if the SA node isn't sending out action potentials, what will happen is the AV node will generate action potentials of its own and send on to the ventricles to keep the ventricles contracted. We can say that the AV node is a subsidiary pacemaker or a backup pacemaker. Kind of like my alarm clocks. Oh my God, an electric alarm clock and a battery-operated alarm clock. The electric alarm clock is set to go off first. The battery-operated alarm clock is set to go off 15 minutes later. Normally, the battery-operated alarm clock doesn't go off because when the electric alarm clock goes off, I shut the battery-operated alarm clock off because it's annoying. But if something happens overnight, like the electricity goes out, the electric alarm clock may not go off, but I've got a backup system that will wake me up a few minutes later than usual, but it will still wake me up. And that's the same role of the AV node. Something happens to the SA node, we can still keep the ventricles pumping. They won't pump as fast as they did if the SA node was driving them, but they'll pump enough to keep you alive. So when the action potential passes through the AV node, it passes down the septum here. First we pass along what's called the AV bundle, also called the bundle of His, named after the feral cat hanging around my place. No, it's actually named after Dr. Hiss, who studied it. Actually, it was named after his wife, Mrs. Hiss. The bundle of His then splits into two branches, the right and left bundle branches. So we're going backwards again. Which takes the action potential all the way down to the pointy portion of the heart, which is called the apex of the heart. Then the action potential is delivered to the ventricular myocardium by conducting cells called Purkinje fibers, named after Dr. Purkinje's wife. The Purkinje fibers then deliver the action potential to the ventricular myocardium, the muscle cells of the ventricles. And once they get there, once you've told one muscle cell, hey, fire an action potential, it will tell all of its neighbors to do the same thing. Because remember, the cells of the heart are connected to each other by electrical synapses, not chemical synapses. And one cell can conduct connected. So my question for you is, once you've put on your thinking cap here, why do we bother to send the action potential all the way down to the apex of the heart before we deliver it to the ventricular myocardium? Why don't we just deliver it to the ventricular myocardium directly out of the AV node?
Contracted it with the base valve.
So you've taken the class before. Yeah, when the heart contracts,